Hi, welcome to Residential Construction Technology. I'm Tom Stephenson, and today we are going to be talking about wall framing. In previous lectures, we've looked at floor framing, we've looked at foundations, and we've looked at sort of the process of getting permits and site layout and site plans and how that's organized. Today our topic continues on with framing. Framing is a big structural component of the construction of a house. It's what we call the superstructure of the house. Everything that's above ground that is structural is generally part of the framing process when we talk about wood frame construction. So we're going to look at the structural elements and components, some of the terminology or nomenclature for walls. We're going to talk about visualizing the materials used and their orientation in a framed wall. And we're going to identify and analyze sound framing methods that meet the minimum standards of the National Building Code and the Ontario Building Code. So those will be the reference points. This is all in Chapter 8 of your textbook, Understanding Construction Drawings, Housing and Small Buildings. So understanding construction drawings, housing and small buildings, as the photograph indicated at the first slide that we started at. And a little bit of it too is referenced to the CMHC wood frame construction book that you also have. So we have wall framing, partition walls, generally known as non-load bearing walls. And by the way, you should be able to know the difference between the different types of walls. So if you hear the term partition wall, we're referring to a non-load bearing wall. Unfortunately, partition walls, sometimes people just call walls partition walls, but really the technically correct name is that it's a non-load bearing wall. So that means it could be there or you could take it out and the structure should be fine. So load-bearing walls are walls that carry the structural load from another component of the house, from the floor and from the walls and other parties that may be up above on other floors. And non-load-bearing walls, which is a partition wall, is only really carrying their own weight. So we have a bunch of members that's involved in walls, studs. Those are the vertical members in a wall. We have plates. Those are the horizontal members that are at the top and at the bottom of the wall. And we also have a lintel. Lintel is the beam that goes over openings like doorway openings and window openings. We call it a lintel. Now, those of you that have construction experience, you're used to hearing the word header. People tend to call it headers on the sites. I believe in the US they just call them headers, but we call them lintels. The technically correct name in Canada is lintels, because when you look up lintels in the building code, that's only for over doors and windows. If you look up headers in the building code, as we said in the last video, then you're looking at a floor opening, right? And so headers carry the weight of joists into them, and then they transfer that weight over to trimmers. So a little bit different terminology. Lintels in a wall, an opening, they're supported on jack studs. So that's a type of stud that's shortened to carry the load of lintels. And cripple studs are shortened studs. Those are like tail joists in a floor are shortened joists. Cripple studs are shortened studs, like might go over where a lintel is supporting or underneath a sill for a window opening, and we call that a rough sill. So probably the best way to look at it is these are cripple studs. They're shortened. These are cripple studs. This is a lintel. These are jack studs. This is a rough sill. And so these are all the components. This is a double top plate. This is a bottom plate. This is all made out of dimensional lumber. So your plates would be 1.5 inches thick. Your studs would be 1.5 inches thick. Your lintels would be sized based on the distance that they're spanning. The wider the distance, the bigger the lintel. Also, how many floors it's supporting above it. Also, what kind of roof loads it's supporting, like snow loads that are on top of the roof, because these loads can transfer through the building and structure. So there's a lot of considerations when we're talking about the design of the components, the beam systems, the spacing of the studs that goes into wall framing. Typical spacing for wall studs is in building code terms 400 millimeters, which is 16 inches on center, pretty close. We've discussed that in the previous lecture. The building code will accept that, it'll say it's a metric. It's only going to be in metric. National Building Code, Ontario Building Code. In Canada, that is our national system of measurement. So it'll be at 16 inches on center that you actually build it, because our plywood, our drywall, all of these things, they come in like 4-foot by 8-foot measurements. And that's because, quite frankly, we ship about 10 times the amount of plywood, drywall to our neighbors south of the border, and they do everything in imperial. So it makes sense that we just use the same sizes. Not that you couldn't get metric sizes, but you probably wait a long time and you pay a lot extra. So here we have a lintel over a sliding door. This is actually in a basement, if I recall, a walkout basement door. And so in this case, the lintel is framed on the top. Underneath, you can't see, there's a plate under there. That's basically what we call a header wrap, and it wraps around the rim joist of the floor, and it wraps out around the other side. And this is actually a weather barrier material. It's a Tyvek material, and we'll talk about that in another class, but it allows for it prevents moisture from coming in, and it allows any moisture that's on the inside to breathe out to the outside. But that's a little bit more complex issue that we'll get into when we start talking about the building envelope. But in order to be effective, we have to put this in during the framing process. So because it has to wrap around as we build things. And so that's exactly what's going on there. But there would be plates on top of this lintel. And so then we've got cripple studs. This is framed kind of opposite to how you see a lot of textbooks indicate it. You'll find that most textbooks will show the lintel right over the door, and then the cripple studs over top of the lintel. Well, at least in the greater Toronto area and most of Ontario, we tend to put the lintels on top. Other provinces may, and I've been to a number of them, they may frame it the other way around. Both ways are acceptable to the building code, so then it's just a matter of preference, because the main thing is that the weight from up above is being taken on so that it doesn't actually that it actually spreads the load off to the sides. So that's very important from our perspective, that the weight that's up above gets distributed onto the lintel, and it transfers those loads to the jack studs, which transfer it down to the floor, which transfers it to the foundation wall, and so on and so forth down to the footings. If you remember when we started talking about footings and foundations, it's really good to look at the structure and imagine how the loads are being transferred. And if there's any spot where that load is not being picked up, you can infer that there will be some sort of structural issue, some sort of cracking, some sort of sagging. So it's good to sort of follow the loads. So we have this way of transference occurring, and the lintel is placed on the top. This is also really good in wall framing practices, because there's a plate up here, and this particular opening, it's a 2x6 wall. It may be using it looks like three 2x10s for the lintel in this case instead of 2. So 3 2x10s would be 4.5 inches wide, 1.5 inches, 1.5 inches, 1.5 inches. Well, a stud, 2x6 wall stud, would be 5.5. So you have a 1-inch difference. That's about that little space you can see in there. So when we frame it this way, the drywall can easily span from this point to the plate up above. That's not a problem there. So we don't have to fill anything in or do anything. If we put the lintel on the bottom, we would have to put in a filler, or we'd have to have another plate just below it. So this makes it a little bit simpler for that installation. The other reason that it tends to happen too is if you ever mess up the opening, it's a lot easier to move this up than if the lintel was there. So there's that to it as well. This would also be easy to insulate too. You could get styrofoam and you could put that on the inside, and that would help to form a thermal break in the wall. Warm moves to cold, and if we have something like insulation, it's better than having wood. Wood's not a bad resistor to heat loss, but it's not a great resistor to heat loss. So when we talk about lintel sizes, as I alluded to, we have what we call the design snow loads. And so this sort of take from 9.422 of the building code gives you sort of an understanding of composite snow loads. So composite snow loads are the wet snow load. There's if you ever go and you shovel snow after it just snowed and it was like -10, the snow's like fluffy. It's nice to shovel. It's very easy. It's not heavy. If you waited a few hours and then the temperature changed and it turned to like a freezing rain and it falls on top of it, each shovel of snow, like it weighs like 40 pounds as it compared to before it was like 3 or 4 pounds. It was just fluff, right? Well, we have to design our buildings to consider the heavy loads because it could snow 2 feet on your roof and then it could pour rain on it. And that's going to act like a sponge and that you're going to have all that weight on your roof. We wouldn't want it to collapse on us. So the building code requires that for different jurisdictions that you design the actual lintels based on snowstorms, 100-year snowstorms with a factor of safety built onto it, and composite snow loads, not just fluffy snow, but composite snow loads. So that's factored into the design. This is a chart from the Ontario Building Code, maybe from the previous version, so you may have to, if you're doing something new, look at the current version. Codes are always being updated, so you got to make sure you're working with the most current version. And this is part 9, and it's saying to use the 0.6 composite snow load in the chart. And you see every town and city, pretty much, this is one of several pages in the building code, is listed, and the snow loads in those various locations. Like the snow load in Trout Creek is way more than the snow load in Toronto. So there's quite a difference. Even Trenton, it's quite different. Trenton's, I don't know, a couple hours away from Toronto. So different jurisdictions, they can be in snow belts and different things where they receive a lot more snow than other areas. And so that's why you have to go with where you're located and the composite snow load. This only comes in if it's like a garage or something where you can use the 0.5. We also have maximum spans. There's a variety of tables in the building code. And like we talked about with joists in the previous presentation, there's a table for lintels. And so in part 9, a lot of things are pre-described. And so this is a lintel supporting and how many floors it's supporting, right? So a roof and ceiling only. So this would be like a 1 floor. This would be a roof, ceiling, and 1 story. This would be a roof, ceiling, and 2 stories. A roof, ceiling, and 3 stories. So it's really based on what you are actually supporting and how many floors of weight you're supporting, and using the snow loads. So if, for example, if you had this at 1, I would be going to the next one, 1.5, and anything less than 1, I would go here, but 1.5. Remember, the building code is the minimum standard. If you go 1 step higher, that's not a bad thing. But from a building inspector point of view and from a buildings review point of view, they're looking, did you meet the minimum standard? So this is what this sets. You can always go more, you just can't go less. So then you would look at this, and this would be the span. And the span is, as an example, from the support to the support. And it wouldn't be this one. This is just a piece of blocking. It would be the jack stud here. So how much is it spanning from here to the jack stud that goes all the way down, not this little cripple stud that's on the side of that jack stud. And so that would give you the actual span that you could that you'd look under. So if you were looking under this, you'd decide, okay, so what span do I have? So let's say I had 1.7 meters. Then I wouldn't use this one. I would go to this one. And so I'd know I've got to use 238 by 184. And that's 2 2x8s. That's what that means, 2 2x8s. We still tend to, on the job site, in the stores, even though everything is metric, we call them an imperial. So this is 2x4, that's 2x6, that's 2x8, that's 2x10, and that's 2x12. If you ever get confused, you can just sort of start at a 2x4 and just go up in increments of 2 inches, and you'll know what each one is. The other thing you can also do to get a sense of the size, approximately 20, it's 25, it's not approximately, 25.4 millimeters equals 1 inch. So you know that pretty much 200 millimeters is 8 inches. And remember we said a 2x8 is not exactly 2x8. It's a little bit smaller. It's around 7¼ inches, 7⅛ inches, depending on the moisture content. So this would be the size in here. Sorry, this would be the size in here. 38 by 184. That would be a 2x8. 38 is the 1.5 inches. And that's how the charts work. And that's how lintels are sized up. And on your drawings, and construction drawings, if you have to build something, you would look at the construction drawings. And on the first page, there's the construction notes, and it's going to tell you the size for the lintel. On the floor plans, it's going to say by the window L5, and that means you would look at 238 by 286 if it says L5, or L4, 338 by 235. So you would actually see that sizing, and that would be the corresponding size that you would use. These other L's here, and we'll talk about that later when we get into masonry work, these other L's are based on the steel lintels if we're using brickwork on the outside. Something has to carry the brickwork over the windows. So we have steel angle irons, and in this case they're 3.5 inches by 3.5 inches by 1/4 inch. So they look like an L, and they're about 1/4 inch thick. If you're not too sure what that I'm talking about with that, you could move yourself to chapter 10 and just flip through it, and you'll see some images of the lintel that goes over for the brickwork. So that's what these are. L7 to L12 and L1 to L6 is for the wood lintels that we would have. Now, if we undersize the lintel, that we can cause sagging in it. So if we don't use the appropriate size for the loads that are being required, it'll cause sagging, which will cause cracking over the doorways, and that's not very pretty. If we don't install the drywall properly, it's more prone to cracking. So this is actually much better. A lot of times I see the drywall and they just go straight up, and they cut a straight piece here and they cut a straight piece there. And you've got a very high likelihood where the joint is coming there that you're just going to get a nice straight crack up there. It won't really crack the drywall over here like here if you have this drywall cut around, and even more is better depending on where your cripple studs are. It's just these little things that are, there's a bunch, there's probably about 500 little things that you inspect when you're building a house, and the little things, if they're done right, like the spokes in a wheel, you know, you get them nicely tuned, it runs smoothly, easily that way. So it's almost like I used to do triathlons. If you have all the spokes in the right order, that'll run smooth. Your project will run smooth. So there's a lot of little things that with experience is helpful. And checklists can really help you to remember all these little things, especially when you don't do it a million times. And even when you do, you forget things or you get interrupted. So how do we do the corners? We usually do the corners so that we can fasten drywall in the inside corners, and so that it's easy for us to do it. There's different ways of doing it. There's 2 stud corners, there's 3 stud corners. Usually the methodology that we utilize is based on the ability to fasten the drywall on the inside, so we've got something to screw it to. The other consideration is if we have less lumber going through the wall, we have less thermal bridging, we have more room for insulation, and that makes a higher effective R value for the wall because your studs and your plates are not as energy efficient as insulation is. So this is actually a 3 stud corner. You can only see 2 of them here. This is one and this is another one, but there's another one in behind this one that's going this way in behind. So you can tuck the insulation in behind that way, and that's a very effective way of doing your insulation and of doing your corners. And you can see there's lots of room here to screw the drywall to. Intersecting wall, I had that in a couple of different slides. This is a pretty good detail to just spend a few minutes and go through it, look at it, try to get familiar with it, pause this video, take a look at it, and get used to the components, how they're placed. You notice there's a brace bracing member. We usually use metal bracing. And that stops the wall from what we call racking. You know, when there's a load and it wants to shift, well, through triangulation, the brace stops it from moving. This is, I think, a lead-in brace. So we'd run a skill saw or circular saw on both sides of a piece of wood, and then we'd chop that out quickly. And then we put the piece of wood very strong. But there's metal braces that are even easier. You just snap a chalk line and you run a saw kerf down, and then you just nail the metal brace in. I'll show you some of them in the upcoming slides. Here's an intersecting wall, and this roll of black polyethylene plastic is placed on the inside, and its purpose is to form a continuous air barrier on the inside, because you're going to put other plastic later on, and you're going to seal it against this plastic with acoustic sealant. So what you're trying to do is seal the inside of the envelope so that you don't get moisture penetration going through the envelope, and that you don't get air leakage. So that's why we call it an air vapor barrier. And it gets a little bit more complicated than that. Usually we have the air vapor barrier combined on the inside, but we can separate them if we want. We can have the vapor barrier on the inside and the air barrier on the outside if we want to. It gets a lot more complicated, to be honest, if we want to get down to building science principles. Layout. So a wall layout, your spacing, like I mentioned, it's going to be 12 inches, 16 inches, 24 inches, or 19.2 inches. Remember, 19.2 divides evenly into 8 feet. So your sheet goods can join up exactly on a stud. When we do openings, it's very important to know that the openings are going to be larger, right? Larger than whatever you're putting in it. If they're not, you got a big problem. So for windows, if I have a 3-foot window by a 4-foot window, my rough opening, we call it the rough opening, should be a 1/2 inch bigger on each edge and a 1/2 inch bigger from the bottom to the top. So that would mean a 3-foot by 4-foot window would have a rough opening of 3-foot 1 by 4-foot 1. And that 1/2 inch we would shim, and that would give us some space to put some polyurethane foam around between the window and the frame to seal it up really well and to insulate it. So our openings on the exterior, we usually allow about a 1/2 inch around it. On the interior, for a door, interior doors, usually you allow 3/4 inch bigger. So you have to know what the door size is. Let's say you want to put a 2'6" door, very common standard size for interior doors, 2'6" by 6'8" by 1 3/8", standard stuff. So 2-foot doors, 2'2", 2'4", 2'6", 2'8", 2'10", very common, very easy to pick up at your local building supply. Many different kind of pressed patterns that you can get. So we've got a 2'6" by 6'8" by 1 3/8" door, interior. If it's an exterior door, it's usually 1 3/4 thick. So if it's 2'6", I gotta allow the thickness of the door frame on each side. So if it's 3/4 and 3/4, that would be another 1.5 inches. So that would be 2'7.5". And then I have to allow a little bit of space for shimming on each side. So I usually allow 3/8 and 3/8. That gives me 3/4 inch overall for adjustments. Because we discussed in lecture 3A, wood. It expands, it contracts, it's not perfect, it warps, it twists. Even if you put it in perfectly plumb, things move a little bit. You got to have some flexibility because you need to put your doors and windows perfectly plumb and level so they don't stick and that they operate properly. So you allow a bit extra on the height and on the width, and it's determined by the materials. So a 2-foot door would have a rough opening roughly around 2'2.5" for the door. So this is a 2-foot door. I used a 2'6" in my example. That would allow 1.5 inches and then another inch in this case for spacing on each side. So that's giving you a 1/2 inch. So somewhere, it depends who's hanging the doors. It's usually anywhere from 3/4 to 1 inch flexibility. You don't want to leave it too big because then that takes too much shims and it's a little bit more awkward to set up. And so you mark the location of all the jack studs. The king studs, they call the king stud the stud that goes beside the jack stud. Most, like the building code doesn't have an official name for king stud. It's just called a stud because it runs full height. But just to differentiate, the king stud runs full height, and that's what your jack stud goes against. So there's some sort of layout marked with jacks and C's. Some people just do X's and O's for studs and shortened studs. Just depends. It's usually just a quick layout way of marking up your studs. And so, as I said, you got that space around that to be insulated, and you're allowing for the extra larger size for that. So keep that in mind. This is a really good sort of illustration here of allowing the extra amounts for the width, right? And that's your little extra amount for shimming. So this is a cross-sectional view. You're looking straight down on it, like you're looking down, and this is the inside edge of the door frame. This would be an exterior door because it's got what we call a rabbeted jamb, and that's where it's cut out in this section, right? In an interior door, we usually just put a door stop against the door where the door closes up against. And in this case, I showed 1/2 inch of shimming on this side, 3/8 from that side. Like you choose one or the other, right? I probably should have just said 3/8 and 3/8 or 1/2 and 1/2 to be consistent. I think I made a little error there, but that's the way the cookie crumbles. And there's your height. All right, and you got to make allowances again to make sure you've got enough room for your, if it's an exterior door, the door sill, your hardwood flooring or whatever finished flooring that you're putting in there, and that you got a little bit of extra space here, and that you can insulate that space, and then your casing will cover that so you won't see it. The casing's going to cover these spaces afterwards because you're going to put the casing on. The casing's your finished trim that goes around the door. There you can see the shims, there you can see the space. That would be then polyurethane foamed. Bracing, as I said, if we're using structural sheathing, we don't have to put bracing. So if we're using like plywood or OSB, we don't have to put bracing. But if we're using like styrofoam on the outside of a building and we don't have a sheathing underneath it, then we either have to do a metal brace or a lead-in brace. So I talked about the lead-in brace already. This is the metal brace, and it just looks like a sort of a T, and it's got a kerf, and then it's nailed at each one, and your wall will be very, very solid with that in place. So that kind of gives you that overview of the wall framing and a little bit of the correspondence for how we utilize the building code in designing lintels. And take a bit of time, go back into the book, try going through the Understanding Construction Drawings text, and if there's questions in the chapter, try answering them, see how that makes sense to you, and slowly but surely things are going to start to make a lot of sense. So we'll be back in lecture 3B to continue on our discussions with wall framing. So this is Tom Stephenson signing off for now, and have a wonderful day. Talk to you soon.